Welcome back. Today is the last lecture in this module. This module is content based recommender system models, and in this regard today we are going to talk about regression models and we will also concluding this particular module. So, this is the content. So, we will be talking about regression model followed by conclusions on recommender system. So, now coming to recommendation system models, so far we have covered 4 models: decision tree, naive based algorithm, then rule based approach, then one more approach we have covered. So, these 4 approaches we have seen that they work well with the response variable, which is basically some kind of binary or in ordinal scale. In fact, for all these systems that we have studied, all the methods that we have studied, the running example that we used was with binary variable. However, there can be situations in which we have the response variable which is a real number. So, in such setting, linear regression is a very good choice. In fact, for large scale problems, linear regression models is a very good choice. So, if you look at this table, we can see regression model and its variations fit with different kinds of rating variable. This linear regression, simple linear regression, multiple linear regression and kernel regression, they fit well with real type, the target variable which is a real number. Then binary logistics regression is for unary and binary rating, and in case of unary rating, it is actually considered as a binary rating where the rating 0 is considered as something where the user has not given any input. Similarly, it can be extended to multi-way regression, and we have something called probit models for unary and binary, then multi-way probit for categorical and ordinal variable, and order probits for ordinal and interval based variables. So, out of this we will be choosing the first one, because we have already seen various classification models which are fitting well with categorical variables. So, therefore, we will be focusing only on linear regression. In fact, we have talked about linear regression on several occasions. While talking about the supervised learning algorithm, we saw one glimpse of linear regression model. Then we also saw about regression models during our discussion on user and item based collaborative filtering, where we were trying to learn the weights using some kind of regression model. So, in the current setting, when we are discussing it in the context of, we are discussing this in the content of content based recommender system, we still will be able to use this regression model. This is the regression model of multiple linear regression. Now, what is your data? Your data specifically in the content based recommender system, where you have text documents. These text documents are represented in terms of TF or IDF rating. Now, this TF IDF rating will be giving you certain numerical value. So, this numerical value represents the feature. So, as per this model, this is your feature 1, this is feature 2 and this is your feature P. So, you have P such features. So, these features may be the TF IDF rating, and if you are thinking of combining it, then it may be some kind of explicit features that we have seen in our last example. And we are supposed to determine this value of y, which is our response variable. Now, in this particular model, we assume this response variable is numeric. So far, all our variables were categorical. Now, this is our model. What the model says? That given the values of feature 1, feature 2 and feature k and these model parameters beta 0 to beta p, if we determine the value, we will be getting the value of y, but what happens? We may not be able to get the exact value of y and there will be some error involved. So, this epsilon basically tells you that residual error, the error term. Okay, so now when we solve this model and determine the estimated values of beta 0 to beta p, then based on this estimate we find the estimate of y, and in our data set we have total n number of observations. So, if we have n number of observations, so how do we get these beta values? We get these beta values by solving this least square problem, where sum of all these differences between the actual observation and the estimated value, we square this and take the sum. So, this error is called residual sum square. So, taking this one, we try fitting this function to some fit this to a linear function, so that we determine these values. And we know that how to determine these values. We know the gradient descent, stochastic gradient descent, etc. But anyway, those things we have already discussed. So, besides minimizing this difference, we also try adding certain penalty term, and because of this penalty term we avoid overfitting. So, this we avoid overfitting. Okay. So, besides this, sometimes to understand which factors are relevant, which factors are not, we set up this with L1 penalty, and as we have discussed in one of the earlier lectures, if we put this L1 penalty, what happens? It enforces, it not only helps avoiding overfitting, it also enforces some of the betas, if they are not very relevant, to be exactly 0. So, which means by this process you will be able to understand in a much better manner which variables are actually irrelevant in your system. Now, moving ahead, these things whatever I told so far in some setting, like how to use regularizer, what is L2 regularizer, what is L1 regularizer, those things we had a bit elaborate discussion elsewhere in some of the earlier lecture. Now the point that we are going to make is, given that we are fitting our model to this regression setting where we try fitting a linear function, how do we draw various inferences? So, first inference we would like to draw is to understand how well does the model fit the data. Second is at least one of the predictors, that is features, is useful in predicting the response. So, we would like to find out the contribution of this in determining the response variable. Then we identify whether all the predictors explains X, explain Y, that is the response, or only a subset of the predictor. Predictor here means that feature. Now, given a set of predictor values, what response values should we predict and how accurate is our prediction? So, these 4 points we are going to discuss now. So, first point is about assessing the accuracy of the regression model. When we assess the accuracy of the regression model, as we have already seen, what we were trying to minimize? We were trying to minimize this residual sum of squares. That was the value of y minus estimated value of y. So, our aim was to minimize this, and while minimizing this, to judge the quality of this, we can quality of the regression model, we can use this RSS in determining two related quantities. So, what are they? One is residual standard error and R square statistics. Now, the regression model associates an error term with each observation, isn't it? Error term with each observation. This was the model, this was the error term. So, it associates this epsilon, which was the error term. So, which means with how many observations we had? We had total n number of observations. So, with respect to n number of observations, with each one we associate one epsilon value. Now, the regression, now what happens? Due to the presence of these error terms, even if we know the true regression line, we would not be able to perfectly predict x. Why so? Because this line is just the average line, isn't it? Suppose in case of a simple linear regression, this is your x and this is your y. So, your points will be, and you will be fitting the line which will be minimizing the error. But whatever you may say, when you actually get a new value of x for which you are going to determine y, that new value of x probably will be somewhere here, and there will always be an associated error term. So, as a result, we would not be able to perfectly predict the value of y from x, even if when we know these beta values, because these beta values basically define this line or a plane in case of a 2 variable regression or one hyperplane in case of a multiple variable regression. Now, this RAC is an estimate of the standard deviations of the error term. Roughly speaking, it is the average amount that the response will be deviate from the true. Now, here also we were finding the deviations. So, what is the point in determining this? Now, this term makes sense because it is a sample. So, therefore, it is multiplied with 1 by n minus 2, where n is the total number of records. Where n is the total number of records. Now, this RAC is considered as a measure of lack of fit of a model. So, if the predictions obtained using the model are very close to the true outcome, value of RAC will be small, and we can conclude that the model fits the data very well. Now, there is one more statistic using which we can also assess the accuracy of the regression model. So, here RAC was supposed to be small when we have a good fit. In case of R square statistic, it has to be large in case of a good fit. Now, RAC provides an absolute measure of lack of fit of the model to the data, but since it is measured in terms of units of y, because it is basically y minus y cap square root over. So, it has the unit of y. So, therefore, we need some kind of statistics which is not having any unit. Now, this R square statistics provides one such alternative measure. What it does? It takes the form of a proportion, so that unit you miss. The proportion of variance explained, and so it always takes the value between 0 and 1 and is independent of the scale of y. So, this is defined like this: R square is TSS minus RSS divided by TSS. So, where TSS is the total sum of squares. Now, see, when you found out this value of RSS, what was RSS? RSS was sum over all n yi minus yi hat. Okay, yi hat. Whereas, when we talk about TSS, it is y bar. So, what is this y bar? Remember your data set. In your data set, you had the features like f1, f2 up to fp, and your response variable was y, and you had many values. Now, when we consider this y of the training pattern, this y values have some average, and there will be some deviation of each of these y's with respect to this y bar. So, what does it indicate? It indicates that originally there is a lot of variation in the data. So, that is what it says. TSS measures the total variance in the response y and can be squared and can be, so total variance in response y and can be thought of as the amount of variability inherent in the response before the regression is performed. So, this variability was originally in the training data. So, this variability was in the original variability in the training data. Whereas, RSS, residual sum of squares, measures the amount of variability that is left unexplained after performing the regression. So, what was it? This was y hat, and we had this RSS, which is basically y minus y hat. Okay. So, RSS measures the amount of variability that is left unexplained after performing the regression task. Now, what is remains unexplained, because let us say this is our regression line, and after the regression, depending on the values of beta that you get, this is the value which got predicted, but this was the actual value. So, this was the variability that was left unexplained. Now, TSS minus RSS measures the amount of variability. TSS minus RSS measures the amount of variability in the response that is explained by performing the regression. Okay. So, this is TSS minus RSS. This explains amount of variability in the response that is explained. Now, what is R square? R square is, what is R square? It is TSS minus RSS divided by TSS. So, what was the original variability? Original variability minus what is getting explained. So, R square measures the proportion of the variability in Y that can be explained using X. Now, an R square statistic that is close to 1 indicates that large proportion of variability in the response is explained by the regression. So, which means it is a good fit. Large proportion of the variability is now taken care of this regression line. The number near 0 indicates that a regression does not explain much of the variability in the response. So, this might occur because the model fit is wrong, or the error variance is high, and many such reasons. For example, suppose there is some kind of outlier in the data, and because of that outlier the line, regression line is getting distorted. So, that may be a reason, and because of the error variance, high error variance also, it may be the case. Now, the relationship between response and predictor. How do we find whether the regression coefficients are 0 or not? So, how many regression coefficients were there? Beta 0, beta 1 up to beta p. Now, to understand the relationship between the response and the predictor, predictor was y, and what was the responses? The predictors were x1 or f1, f2 up to let us say xp. For the features f1 to fp, the values are x1 to xp, and y was the predicted value. Okay. So, now under what condition you say that y has a relationship with x, with x has a relationship y. This is beta into x1, beta into beta 2 into x2 and so on, and beta p into xp. You take the sum of that. So, which means if any one of the beta is 0, it indicates corresponding x value does not have any kind of contribution in y. That is why beta 2 is being forced to be 0 or near 0. So, therefore, in case of a multiple variable setting, we need to check for all this, or in general we have to test some hypothesis that all these values beta 0 equal to beta 1 up to equal to beta p, all of them are 0. So, we will be talking about hypothesis testing when we talk about the performance and all, but for the time being, let us say this is our null hypothesis, and there is typically there will be two hypotheses. One is null hypothesis, and one alternate hypothesis. So, our null hypothesis is all these are 0. Now, if any one of these is not 0, how do we know? Do we have to individually check? No. there is another statistic called F statistic. Using this F statistic, we can say when there is no relationship between response and predictors. So, now this F statistic is defined in this way. This TSS, RSS, etc. you already know. N is the number of records on which you are performing regression. P is the number of attributes. So, this way you have n number of records, you have p number of attributes, p attributes. Okay. So, you have p number of attributes. So, when n is large, when there is no relationship between response and predictor, one would expect F statistic to take a value close to 1. Otherwise, F is always greater than 1. Now, how large? It depends on the data set. When n is large, an F statistics that is just little larger than 1 might provide the evidence of the relationship to exist, whereas when the size of n is small, it can be very large quantity as well. So, next question we asked, how to decide the important variables. So, we can decide on important variables by feature selection, and many feature selection methods we have already studied, but with respect to regression, particularly we have talked about stepwise regression. So, stepwise regression we studied in a bit detail at the time of feature selection. So, this stepwise regression, you can have forward selection and backward elimination, where in case of forward selection you start with one feature and keep on adding. Otherwise, if you have total p attributes and taking one attributes p, taking two attributes p, c, 2 and so on, total you may get 2 to the power p number of combinations. So, therefore, to avoid this forward and backward selection and backward elimination were adopted, where you start with one feature and keep on adding, so that your performance improve. Now, the performance, the statistics, various statistics which were used to judge the quality of the model or the performance of the model, we saw last time. Besides, of course, RSS and RSE, we have this Mallows, CP, Akaike information criterion, Bayesian information criterion and adjusted R square. These things also we have already discussed. So, all these values, they actually give some kind of penalty in terms of number of attributes, number of attributes to be determined, on which it is to be determined. So, the next thing is we have to judge the uncertainty associated with the prediction. Now, when we know that we are actually fitting a line or a plane or an hyperplane. So, which means if we determine the corresponding beta values, we determine that it is a good model, is it sufficient? No, because the original model that we considered was having some error. Y was beta 0 plus beta 1 x1 up to beta p xp plus some epsilon. So, that epsilon is some error which will always be there even if you correctly determine with right optimization, you determine the values of all these betas. So, this is called irreducible error. So, whenever this error is again going to come when you estimate, when you get the estimated values of beta 0, beta 1 and beta p. So, when you get the estimates, how do you get the estimates? By solving that least square problem. So, even if when you get the estimates and you get a good fit, then also you cannot avoid this term is going to be there. Okay, so this part is called irreducible error or the model bias. Now, when we use a linear model, we are estimating the best linear approximation to the true relationship. Here we ignore this discrepancy and operate as if the linear model was correct. So, we assume that the linear model which we create using this estimated parameter is actually correct. So, to understand how well we are taking care of this irreducible error or how well we are taking care of this estimation, we ask some questions related to the prediction interval. This prediction interval typically will be little larger than the confidence interval. So, these are few potential problems in regression modeling which we would like to see one after the other. So, first problem is non-linearity of the data. Remember, through regression what are we trying to do? We are trying to fit a linear model, but it may so happen that the data is actually not giving a linear relationship. There are of course other measures, like you can have nonlinear version of the regression, you can have little more complicated network kind of thing like neural network and all, but right now focusing on only linear regression, if we find that it is not a good if it is not a good fit, how do we know? To know this, we have to look for the residual plot and find out if there is any pattern. For example, here what is the basic assumption of a linear regression model? These are the random errors. So, because this epsilon is a random value, it has to be distributed without any pattern. However, here on this, if you try plotting, you are able to get some pattern. So, which shows there is a lack of fit with the linear model and it is some kind of nonlinear model you must try. Still, you can, in a way, you can think of reducing this effect by transforming y in certain manner. For example, in this second one, this y is transformed. If you have a log transformed y, this is supposed to be sorry. So, in this you have actually tried a quadratic fit. So, if you try a quadratic fit, then these errors are more or less becoming pattern free and more or less they are random. When you try fitting a data, it is almost a line. There can be correlation of the error terms. Now, what is the implication of the correlation? If the error terms are correlated, this kind of thing often happen when you have the data, when you have the time series data. So, if the error terms are correlated, we may have some kind of see, we measure our confidence on the model. There are many ways we can say whether it is a good fit or not. But with this correlation, because two variables are contributing in the same manner, unnecessarily this confidence will go up. Okay? So, because our confidence will go up, we will be erroneously conclude that some of the parameters are statistically significant, which may not be the case. So, these correlations frequently occur in the case of time series data, which consists of observations for which measurements are obtained at discrete point in time. In many cases, these observations are actually these observations over the time are actually related. So, that is how you end up in such kind of pattern. So, what do you do in this context? You can actually see how the error is getting changed over the time. So, if you plot that, you will be able to get some idea about this. With respect to time, you plot your error term. Now, there is one more assumption in linear regression model, that error terms have constant variance. They are random and their variance is constant. Now, the standard error, that is RAC, that we determine, as well as confidence interval and various hypothesis tests associated with the linear model, generally rely on this assumption, because every time you are taking y minus y bar or y minus y hat square. So, all these terms relates to the variance. So, every time, so if you have such kind of non-constant variance, it is going to create problem in such calculations. So, as a result, you will end up getting wrong inferences based on these values, like standard error, confidence, etc. You will be getting wrong inferences. So, this non-constant variance in error term, if exists, this problem is called the heteroscedasticity problem. Okay. So, we can identify the heteroscedasticity problem in our data if we get some kind of funnel like pattern in the data set. However, if we try making some transformation, for example, here we log transformed it, the response variable, and this is somewhat reduced. The next problem is that of outliers. Now, existence of outlier may have little effect on least square fit. For example, here in this diagram, we can see this red line is with the outlier, blue line is without the outlier, but there is hardly any difference. But this may not be the case all the time. You may get even a completely different fit, which is not that of same as that of when you remove the outlier. It is also possible. However, this outlier can also otherwise impact the standard error, confidence interval, etc. Now, typically this outlier should be removed, but just like that, blindly removing them is also not good. So, if you remove them, how do you identify? So, while discussing pre-processing steps, we know that we can outrightly find out the outliers before even applying this regression. We can find out the outlier. How do you do? You will look at box plots. Then in case of multivariate, we look at some kind of Mahalanobis distance measures and so on. However, we can also detect it from the residual plots if we are trying with regression. This is the 20th point, which is actual an outlier, and you can also get it observed from the residual. So, now the problem here, the issue is here you have only one variable, so you can visualize the outlier. But in case of a multivariate setting, residuals always are going to be one thing through which you will be able to determine the outlier. Next problem is your collinearity. Now, collinearity refers to the situation in which two or more predictor variables are closely related to one another. The presence of collinearity can pose problems in the regression context, since it can be difficult to separate out the individual effects of collinear variables, because they are basically indicate the same thing. So, now the collinearity reduces the accuracy of estimates of the regression coefficients. It causes standard error to grow. So, now next question is, how do you detect this collinearity? This collinearity, first thing is that you can detect the collinearity by looking at the correlation plots. In the correlation plots or the correlation matrix, if some value is close to 1, or in a correlation plot if the you get a straight line, then you know that there is collinearity between two feature vectors, the predictor variables. Whereas this may not be the case always. So, it may so happen that this may not be visible from this, because this correlation matrix and the between two predictors, that the scatter plot that you make. So, both these are between two variables. It may so happen that even if between two pair of variables there is not much correlation, as such with multiple variable can be high. So, and also give misleading results. So, such problems are called multi-collinearity problems. So, these multi-collinearity problems can be determined by computing something called variance inflation factor. So, for smallest possible value of VIF, that is 1, it indicates complete absence of collinearity, but higher values indicate how much collinearity you have in your among your features. So, with this we complete our topic on various types of models that can be used in recommender content based recommender system. But we may have to note that these content based recommender systems are actually some kind of supervised learning systems, where you have a number of features and one dependent variable. So, once your data set is ready, by combining the item features and user preferences, you can use any kind of the shelf classifiers. So, these such kind of methods particularly use very less engineering effort. And the kind of models that we have used, starting from naive Bayes, then we did rule based and so on, your decision trees, and even regression. Regression, these weights on the coefficients can tell you, explain you which variable is important, which is not. Looking at the regression coefficient, you can decide. So, all these are quite explainable methods, and because of which you can provide some kind of explanation in a content based system. Look, in case of collaborative filtering also, you can provide certain explanation. For example, if you are watching comedy movies, then on that category only you are getting recommendation that can be written. But in the feature level explanation will be missing, because you are not considering feature level details in case of your collaborative filtering. Collaborative filtering relies only on the rating data. So, therefore, item level features, for example, in the running example that we are using, what were the item level features? Item level features were director, the genre, then language and so on. So, you may start getting, suppose you keep on watching Telugu movies, because it is one of the feature of the item, it is not based on the similarity, it is a feature of the item. So, you may keep getting recommendations on Telugu movies. So, besides these two, another advantage is it takes care of the cold start problem at the item level. In case of collaborative filtering, we have cold start problem for both new user as well as new item. In both cases, sufficient ratings will not be available and we completely rely on the rating. But in case of content based system, we are having item features. So, when a new item comes, you can at least compare it with other items, consider its similarity and push them into recommendations. And once they start appearing, what is cold start problem? Cold start problem is you cannot make arrangement automatically pushing some value to the recommendation process, pushing some item to the recommendation process, but you will be do so by simply comparing the item level similarity. So, item level cold start problem is taken care of. So, there are many issues with content based recommender system as well. So, they suffer from over specialization. So, which means if you are watching comedy movies, you will keep on watching comedy movies. So, novelty, which is about getting recommendations on newer items, and serendipity, which is about getting very surprising ones which is beyond your attributes, preference of the attributes, that cannot happen in case of content based system. So, some of the ways in which you can avoid it is by filtering out some of the very highly recommended item and going for the lower one. And you can also introduce this novelty and serendipity in an operational way at the time of programming. So, by including certain random information generator, then implementing something it relates to user profile, implementing poor similarity measures that will capture anomalies and exceptions, and by reasoning you can introduce this. But anyway, as we have already told, it cannot really take care of the cold start problem for the new user. So, these are our references. So, this regression model basically I have talked from this second book, and details of which recommendation algorithm will go for which kind of data we got from here. And this is one reference which you can read to find out what are the recent trends in content based recommender system. So, as we course becomes old, probably this number you have to, this year, beyond this year you have to look for better references. So, these are our conclusions. Regression is a very good approach in the sense it can fit to different kinds of rating scenarios. To judge the quality of fit, we use R-square statistics and standard error. We saw about various potential problems and how they are going to affect the results, and we completed this module with a discussion on content based system and understood that there are certain advantages and disadvantages. With this we finish. Thank you.